Okay, hello. Now it's time. It's 15 minutes after 1. So it is the second lecture that is about these DSPs that we introduced last week. So we had a short introduction about what are these digital signal processors, what are the main application of these DSPs nowadays, and about the basics of what is the main idea, what are their advantages in comparison to the conventional microprocessors or microcontrollers. Now we will go further and describe in detail how this architecture of a DSP looks like, what are those executional units that are different from the conventional executional units that you have on general purpose CPU or on microcontrollers. But just to remind you where we stopped last time, the last time we were discussing the number representation in DSPs, what kind of number representation they use. And we said that we have fixed point representation. So this here is a fixed point representation where I have, for example, 2's complement or unsigned representation. If it is 2's complement, then the weights of individual bits in this 2's complement representation is 2 to the power of 0, to the power of 1, to the power of 6. And the most significant bit is actually a signed bit. It has the weight of -2 to the power of 7. So if this bit is set, then you have to add -128. So 2 to the power of 7 is 128 minus sign. So actually the value of 1 with all zeros is equal to -128 in the case of 8-bit 2's complement representation. Very similar thing is fractional representation, and as we said, it is only something in our head, in our mind, but it doesn't make any difference in the actual implementation. You have a conventional full adder. In the case of 8-bit representation, it would be 8-bit full adder. It doesn't matter if you have this denominator that is equal to 128 or not, because this denominator, this scale, is only in our head. So if I divide this 2's complement number with 128, in this case, the biggest negative number would be -1. 128 minus over 128, so this is -1. And the largest positive number is 127 over 128, so almost 1. In this case, I have a fractional representation, and this fractional representation would represent numbers in the range from -1 to +1. And in this case, we call it Q. Q as a fractional, Q because as a quotient. This Q comes from a quotient. So fractional representation, Q 1.7. I have 1 bit, 1 integer bit, actual assigned bit, and 7 fractional bits. That is the reason I would denote this representation as Q 1.7. Okay, of course, in the actual DSP, they have a much wider data register, much wider data path. So not only 8 bits, typically it is 16-bit or 32 bits. So this fractional representation in that case becomes Q 1.15 or Q 1.31. Okay, but nevertheless, the data range is still the same, -1 to +1 if I treat this number as a real number. But if I would like to have a larger dynamic range, not only -1 to +1, but maybe -2 to +2 or -4 to +4, I simply shift the position of a decimal point to the right. But again, all this shifting is only in our head, in our mind, because the position of a decimal point is imaginary position. The actual hardware doesn't know where this decimal point is placed. Okay? So, for example, if I would like to have this 3 integer position, then this representation in the 16-bit case will be Q3.13. Again, I have 16 bits, but 3 bits will be integer bits. Okay, and 13 bits are fractional bits. So that will be Q3.13 representation. It doesn't matter in the hardware aspect. The hardware is always the same. The adder is always the same. The multiplier is always the same. The only difference is how we treat this number, how we recognize the value that is stored in the register, how we recognize this value. Okay? Going on, the last version, the last data representation that is also available in DSP processors, is floating point representation of numbers. In this case, I have a separate mantissa and exponent. This mantissa is a normalized mantissa, some value that is between, for example, 1/2 and 1, or 1 and 2, depending on the standard. So for some standards, this mantissa is normalized for the range from 1 to 2. For some other standards, this mantissa is from 1/2 to 1. And this mantissa is multiplied by the exponent 2 to the power of exponent. So this 4-bit example, in this example on the whiteboard, on the slide, these 4 bits encode the exponent of this 2 to the power of exponent. And this exponent is multiplied by mantissa. Okay, 2 to the power of exponent is multiplied by mantissa, and I get the floating point value. Of course, the main advantage of this floating point representation is that I have much higher dynamic range. The numbers can be in much higher range from the largest negative to the largest positive value, because the range is determined by the exponent and by the width of this exponent word. While the accuracy, how many accurate decimal numbers I have in the representation, or binary numbers, this accuracy is determined by the width of the mantissa. If I have wider mantissa, then I would have high accuracy of the number representation. Okay, if the mantissa is of limited width, then this accuracy is lower. What I have is, for example, for the single float representation that is standardized with this IEEE standard. So this IEEE 754 standard standardizes this kind of floating point representation, and they have 2 such representations: single precision floating point, double precision floating point, and they also have quad precision floating point. Normally, single and double are used in typical architectures for the CPUs or DSPs. And this single or double, they have, in the single case, 4 bytes to represent floating point number, 4 bytes, so 32 bits. Or for the double floating point, they have double, of course, so 8 bytes to represent this number. And obviously, the dynamic range as well as accuracy is increased in the case of double floating point in comparison to the single floating point, because the width of the mantissa is increased and the width of the exponent is increased. So both are enlarged, just to be able to represent a larger dynamic range of numbers and higher accuracy of the numbers. Okay, but nevertheless, usually DSPs do not have floating point units, because these units are expensive in the sense of implementational complexity. To implement floating point unit on a silicon, you need much larger number of transistors, much larger number of gates. And once you compute some multiplications or additions or quotients, divisions with this unit consumes the power that is proportional to the, as we said, to the frequency. So how many operations do you have in a given time period? It is proportional to the number of transistors changing state. So if you have a larger number of gates that are necessary to implement these executional units, then you would have proportionally higher power consumption, because in order to compute this floating point value, much larger number of gates must change state, okay, for each of these computational cycles. And that is the reason why fixed point implementation is preferred if you want to have a power efficient implementation of DSP algorithm. If the algorithm can be adjusted, implemented on fixed point architecture, it would always be more energy efficient than floating point version. Okay? Finally, we have the extended precision. And extended precision, if I want to describe it for the simple case, for example, if I have this 3-bit representation, 2's complement, Q1.2. So Q1.2, it has values from -1 to plus 0.75. Because this was -4/4, and this was plus 3/4. So it is just 2's complement value, 3-bit value in the range -4 to +3, but divided with 2 to the power of 2. So in the denominator, we have 2 to the power of width -1. The width is 3, -1 is 2, 2 to the power of 2 is 4, so denominator is 4. And then we have this range -1 to plus 0.75. And this representation would be denoted as Q1.2. Okay? So if I have such a representation for the signal, X of n, this signal is delayed here, so the same Q1.2 representation is here as well. This is X of n-1, previous input sample, or X of n-2, sample 2 steps before. Okay? And these values are multiplied by coefficients. So this is H0. This here is coefficient H1. This one here is coefficient H2. These coefficients are also represented as fractional numbers. So this H0 is also Q1.2 value. Some value in this range, -1 to plus 0.75. The same is for H1, the same is for H2. Okay? And then if I multiply these two values, then of course the product is of double width. So multiplication produces the product that is twice the width of the arguments. So normally the product of two 3-bit values is a 6-bit product. In the case of fractional representation, as we described the last time, we have to shift the result 1 bit to the left to get rid of this double sign bit. Because when you have 2's complement representation and multiply two numbers, we always get a double sign bit. And to get rid of this double sign bit, if I use the fixed point multiplier, I have to shift the product 1 bit to the left. In this case, the decimal point is placed again after the first bit. So I would have the product that is Q1.4. So after this left shift, I have the double precision I can denote it with this double line, double dash. So I have this double precision Q1.4 as a result of multiplication of two arguments. Q1.1 XOR n is multiplied by H0, that is also Q1.2. And after multiplication, I have Q1.4. Now, I have to accumulate these products. And this accumulation, so this here is also Q1.4, and this here as well, Q1.4. So one way of doing this is to reduce this double width word to a single width word, and then add this value in a single width adder. So to have this adder that is the same width as the input signal or as are the coefficients. And in this case, I would need a quantizer. So here I would put a quantization unit, and this quantization unit would quantize this double word to a single word. So the result of this quantization would be single precision Q1.2. So Q1.2 as a result of this quantization. So how this quantization is done? It is actually one way, the most simple way is simply take the upper word of the double word result. So this Q1.4, if written in a 6-bit register, it has this 0 least significant bit that was inserted when we did this left shift operation. Okay, so this Q1.4 is positioned where? It is positioned, so this is the sign bit, then I have the 2 bits of the upper word, and I have 3 bits of the lower word, but this bit is always 0 because this bit was inserted from the right side when we did this left shift by 1. So this is this 1, and these are the 4 fractional bits. And that is the reason why we have this Q1.4 representation, because this is this 1, and this is the 4 fractional bits, Q1.4. Okay, and if I want to do the quantization to the single word precision, I simply take the upper word and reject or truncate or simply remove the lower word. I reject this lower word. And I get the result. So the result is simply the upper word. And this truncation would produce Q1.2, this upper word, and the error would be always negative. The actual value after truncation is always negative. It is less than the real value, less than the proper full value. How much less? It is at most one least significant bit of the upper word. Because if I have this 111 here as a lower word, and I reject this word, I simply throw it away. This 111 is almost the same as 1 on this position. So this 11111 is almost the same weight as the last binary position of the upper word. So I have always this negative error that if I do this truncation. In MATLAB, this operation can be simulated with a function that is called floor. Floor, because you take the lower value, always lower integer value. I say integer because in this context, this is the fractional part and this is the integer part. Okay, so this truncation ignores this fractional part, takes only the integer part, and the error is always negative. The alternative to this is rounding. So instead of simply rejecting the lower word, I can check whether this lower word is greater or equal to half, 1/2. So if this first bit is set, then this fractional part is at least equal or larger than 1/2. And in this case, it would make more sense to take the first larger integer value as a better representation of the product of this double word format. Because in this case, this fractional part, so the representation of the lower word, is larger than 1/2. So it is better to round up the upper word, so to increase the upper word by 1. And this is the rounding operation. So in MATLAB, this rounding operation would, as soon as this is 1/2 or larger, increase the integer value. So for example, 3.5 would be rounded to 4, because I have this 0, 1, 1, and I have this 1, the first fractional bit is set, and that means 2 to the power of minus 1. 2 to the power of minus 1, and in this case I do the rounding, and this rounded value is 4. In this example, this 4 is illegal value, actually, because the largest positive value would be 3. So this would cause a wraparound, and this value would be actually be minus 4. And there is a special hardware in DSP that takes care of this. And it would not allow to have this to happen. So if you would have this kind of situation, that the result of rounding operation or addition or whatever causes overflow and causes this kind of wraparound, that positive value becomes negative, it will automatically saturate this value to the largest positive value. We will discuss this separately. So, but nevertheless, we can understand this operation of rounding. This operation of rounding in MATLAB, you have simply function round, value x, and this function here is function floor in MATLAB. If you want to simulate this operation in MATLAB, you take floor of x, and it will take only the integer part of the real number. The first lower integer value would be chosen from the real value. This here is round, but this round is the same, round of x is the same as floor of x plus 1/2. So if I add 1/2 to the value of x and then do the floor, it is the same as if I would round the x value. And that is the simplest way how this rounding can be performed, how this rounding can be simulated in software, in C. So if you want to simulate rounding in C, you simply have to add 1/2 to this register, okay? In this example here, let's write another example. So for example, 0, 1, 0 is the upper word, and this lower word is 1, 0, 1, okay? And now I want to round this lower word into the upper word. The only thing I have to do is I simply have to add 1/2. This 1/2 is 0 upper word and 1 lower word. So this is equal to 1/2. So this is x. And if I add this together, I have the sum. So 1 and 0 is 1, 0 and 0 is 0, 1 and 1 is 0, and 1 carry. So this 1 carry then causes 1 and 0 and 0 is 1. 1 and 1, 1 and 0 is 1, 0, 0 is 0. So now I have this result, and then I truncate the lower word. So after adding 1/2, I truncate the lower word, and I get what? I get the rounded value. So this here is rounded value of x. In our case, so it is value 3, because this fractional part was larger than 1/2, or larger or equal than 1/2. In our case, it was equal to 0.625, because this is 0.5, and this here is 0.125. 1/8. So this third bit is 1/8, the first bit is 1/2, and if I have this value together, it is 0.625. So since this fractional part is greater or equal to 1/2, I do the round up, and this value of 2 is then increased to 3. Okay, so this is the rounding. This rounding is performed in hardware as a part of the multiply instruction. We will later on show that we can invoke multiplication, but with rounding. It will automatically, after performing the double width product, so after computing the double width product, the 1/2 would be added to the lower word after shifting to the left, of course. So if I operate in a fractional mode, I always perform this shift to the left by 1 position if the multiplier is performing in a fractional mode of operation. So after this multiplication and shifting, I add this 1/2 to the lower word and compute the proper value, the rounded value of the upper word. And I use this as a result of multiplication. Okay, but going back to the original idea. So we started from this architecture of digital filter. So we have the filter states, what are actually input samples that are delayed by 1 step, by 2 steps, and so on. These filter states are multiplied with coefficients, H0, H1, H2. But after multiplication, I have to reduce this double width word to a single width, and I do the error. So I have this error of quantization. I insert the error here, I insert the error here, and I insert the error here. So each time I do the quantization, I insert error. This error in the case of rounding is equal, in the worst case, plus minus 1/2 of the least significant word of the upper word. So this Q1.2, this least significant word of the upper word, least significant bit of the upper word, plus minus 1/2 of this bit is the actual error of rounding. It was demonstrated here. So this rounding, this 3.4 is rounded to 4, and the error is 1/2. The error is plus minus 1/2 LSB. So this is the error of rounding. The error for the floor operation is always from 0 to minus 1 LSB. So the error is always negative or 0. Okay? Then, going back to this first figure, so the question is, the question is, why would I do it this way? Why I would insert the quantizer first and then the adder? Of course, the reasoning is, in this case, I have a single precision adder because the architecture is single word. My architecture is 16-bit, for example. I have 16-bit adder. But the alternative would be to have a double-width adder. Why don't you use double-width adder? And then first add up these double-width products together. So the idea is, take this Q1.4 value in the full precision. So take the full precision, Q1.4. And add this in the adder. So this is adder. Double precision adder. Double precision adder. So this adder, in this case, would be like a 6-bit adder. I have a 6-bit adder that is capable of computing sums of such double-width products. So the result would be Q1.4 again. But there is also one problem here. If I have these multiple products, 1, 2, 3, or whatever, 100 products, there is a risk that these products do not fit anymore the fixed width of this adder. So this adder has a fixed width of, in this case, 5 bits or 6 bits, doesn't matter. If I have too many such products, this sum does not fit into the width of the total accumulator. And the solution is, so why don't you extend this adder with the bits? So bit extension. Why don't you add some additional bits to the left of this adder, of this accumulator, to take care of this overflow? If you add multiple products, 100 products, in this case I would add, for example, 7 bits. And these 7 additional bits on the left side are sufficient to take care of 100 such products. I don't have to bother about the overflow. Okay? So the idea is, for example, I extend this precision to be, for example, Q, as I said, for example, 8 or 7 bit, doesn't matter, 8.4. So I add additional 7 bits. This extension to the left side, how many bits I add to the left side, only depends on the goal. So if I want to add 100 values without bothering about the overflow, I must have at least 7 bits to accommodate for such 100 products. Okay? In the actual implementation that we will illustrate for the DSPs that we will be considering on the course, this kind of architecture is used in the MAC unit, because this MAC unit multiplies two 16-bit values into 30-bit product. So this double word, 30-bit product. Actually, this would be Q1.15 multiplied by Q1.15, and this would give the product that is Q1.30. And this product is accumulated in an accumulator that has 8 extension bits. So 8, 16, and 16. With these 8 extension bits, I can accommodate for 256 products without fearing that this overflow would occur, without any risk of overflow. And for that reason, the total width of the accumulator is 40 bits. And the representation would be then Q 9.30. Q9.30. So I have this additional 8 bits on the left side to take care of the overflows. In this case, I don't have to bother about the overflow. Otherwise, if I don't have this extension, I must make sure that these coefficients here, H0, H1, H2, are scaled properly, that are limited in magnitude. Since the value that is on x n minus 1, this value is plus minus 1 for the fractional representation, plus minus 1 in the worst case. So then I ask myself, what is the total, the worst case value for the sum of products? Since these coefficients are also plus minus 1, theoretically, plus minus 1, because they are also fractional numbers. So then each of this product would give a product that is, again, plus minus 1. And if I add n such products, then this worst case sum of products is either plus n or minus n. If I want to make sure that this sum of products does not exceed maximum value, plus minus 1, it is sufficient to have this condition ensured. This condition is that sum of absolute values of filter coefficients must be less than or equal to 1. So if these impulse response samples added together, absolute value of impulse response samples, if I add them together, if this sum is finite, less than 1, then no overflow can occur. No overflow can occur. So I can be sure that the output value would be scaled, would be within the range of plus minus 1. Otherwise, if this HI, so if these coefficients HI are not limited according to such inequality, I don't have the control. So what is the maximum range of the filter output? And the only way to handle this overflow is this kind of extended precision, where I add additional bits on the left side of the accumulator to take care of the overflow. This extended precision is a typical part of the multiplier adder architecture that you can encounter in DSPs. Okay. Then going back to the presentation, we can maybe say a few words about the history of these DSPs, how these DSPs were introduced. I have already opened here Wikipedia web page. So if I type in digital signal processor Wikipedia, you would get a nice article about the history about these DSPs, how they started. This history part is here, third section. So it says here that it started all from the so-called bit slice chips. So even before we had single chip CPUs, CPUs were implemented using dedicated hardware, state machine, and this state machine was controlling the data path. And the data path was implemented using the bit slice chips. So bit slicing, it says here, technique for construction of a processor from modules of smaller bit width for the purpose of increasing word length. So these bit slices were typically 4 bits wide or 8 bits wide. And if I would like to have a CPU that has, for example, 32-bit data path, I would just add these slices together until I have the desired width. So it started from this basic idea. So to have the data path constructed from multiple slices. And some early implementation of DSPs was actually done using such chips. As, for example, our professor Branko Jeren from our department, his PhD that he did was actually about implementing one such DSP using exactly such bit slice chips and state machine implemented with conventional TTL logic circuitry. Okay? The motivation maybe for these DSPs was primarily related to data compression, especially for speech communication, so for transmitting speech in a digital form. And two researchers from Japan, NTT, Nippon Telegraph and Telephone, Itakura and Saito, these two guys invented the so-called linear prediction coding of speech. Linear prediction coding of speech, or LPC for short. It says here, linear predictive coding of speech. And it was an algorithm used to efficiently encode speech, as we already explained on the last lecture, that practically these DSPs are integral part of each of your mobile phone sets. because these mobile phones implement this speech encoding and decoding compression in order to achieve compression, such that the data rate, these bits that are transmitted over the radio broadcast channel, have as least as possible rate, because this rate was a limiting factor for the early mobile communication system. So this mobile communication system limited maybe to 13 kilobits raw data rate or 19.6 kilobits if you include the channel code as well. And for that reason, the speech had to be compressed. And the idea of this linear predictive coding, so this LPC, was how to efficiently encode speech with lower number of bits than you would have at the output of AD converter connected to the microphone. So how to encode this information. And to execute this algorithm, to perform this algorithm, they had to do it on some processor. And this processor had to, well, the idea is the architecture of this processor had to be tuned or had to be adjusted to efficient implementation of such algorithm. And that was the motivation for the birth of the DSPs and for this specific architecture that you can encounter in DSPs. Okay? Then these DSPs are nowadays used in many systems, but it started from this motivation. One of first such DSPs was used to have a speech synthesizer. So it was used in toys, in children toys, to have a speech output. For example, in some toy, and in this case it was to learn spelling. So you would type in some word on this keyboard and it will spell out, so it will produce synthetic speech how the English word is spelled. And this chip was designed in Texas Instruments in a company by three guys, Paul Breedlove, Larry Brentingham, and Gene Franz. The ideas used in this early chip were then used to design the first DSP from this company, Texas Instruments. This first chip is also mentioned here, Texas Instruments 32010 in 1983. So almost 40 years from today, we had this first DSP that was based on the ideas used in this processor for toys, for speech synthesis. But the first single chip DSP was not this one, Texas Instruments 32010. It was one from the AT&T company in US, Bell Laboratories, and one from NEC company in Japan. It is mentioned here. So in 1980, the first standalone complete DSP, so it was all implemented in a single chip. The first standalone CPU that is based on DSP architecture was this Nippon Electrical Corporation, this NEC Micro PD 7720, and the one from AT&T. This is this Bell Laboratory, at that time the largest telecom company in US, DSP-1. So DSP-1. So these both were a single chip solution and presented on some conference in 1980, so 40 years ago. A more modern version of these DSPs was this 32010, and that was year 83. And in year 88, so 5 years after this processor was available on the market, my final diploma thesis was based on implementing floating point library using exactly this one, this 32010 DSP processor from Texas Instruments. Okay, so going back to the presentation, I encourage you to read this information on Wikipedia. It is not that long, but it is interesting to get the insight how this whole branch of digital electronic was developing and motivations that started this DSP architectures. Okay, going back to the presentation. So it is also written here, this DSP1 from AT&T, the year is 1980. Then as a more advanced architecture was this 32010 from Texas Instruments in 82 as a first generation, and this next 7720 is also written, is also shown here as a first generation DSP from this Nippon Electrical company. And in the mid 80s, we already had this second generation DSP, and 320C25 was this really nice DSP from Texas Instruments that was based on advanced version of this 32010, but modified in a way that it was implemented in CMOS. So this C comes from the CMOS implementation. The original one, this 10, was initially implemented in MOS technology, not CMOS but MOS. And for that reason, the single 5-volt power supply was not sufficient. You had to have another, I think, 12 volt as an additional power supply. And this C25 was in CMOS, and it was the first CPU DSP that was a single chip powered from a single 5-volt power supply. At the end of 80s, at the beginning of the 90s, we already had third and fourth generation and so on. Nowadays, typically you would not see DSPs as a single chip, as a dedicated CPU, single chip CPU. More or less, they would be usually part of a larger system on chip solution. For example, as a system on chip that is used in your mobile phone, in a smartphone. And besides 8 cores or 4 cores that you have with ARM CPUs that execute the operating system and applications, you have additional cores, these DSP cores, that are used for real-time signal processing within your mobile phone. Now it's 2 minutes past 2, so we will make a 15 minutes break. If you have any questions, you can answer the questions during the break using chat or using Teams. But this YouTube channel will continue emission even during the break. Okay, 15 minutes break. Okay. Going further, so as we said, nowadays we have these DSPs as an integral part of the system on chip solution on chips that we use in nowadays mobile phone data sets. Okay. For example, the company that produces this, one of the most widely used system on chip is this Qualcomm, American company that produces this system, the main chip that is integrated into iPhones or whatever mobile phones that you have. This Qualcomm, besides having typically 8 ARM cores, out of these 8 cores, they would use 4 cores that are energy efficient cores that are designed to run at slower clock speed and have a higher energy efficiency. On the other hand, if they need really high computational power, then they would activate 4 other cores that are high performance cores. So altogether they have 8 cores, 4 are these energy efficient cores, and other 4 are, for example, high performance cores. But besides these 8 cores that share the more or less similar ARM architecture, they have 3 DSP cores, and these DSP cores in the case of Qualcomm chips are called Hexagon DSP processor, and these 3 cores can run simultaneously in parallel to the 8 cores of the main CPU, let's call it, and each of these cores, DSP cores, can execute some of the real-time data processing tasks. For example, speech coding, decoding, video coding, decoding, or processing of the signals from the embedded sensors in your mobile phone. Because in mobile phone, typically you have many sensors. And for example, these inertial sensors that measure the acceleration in each of the 3 axes, or they compute the position based on this acceleration and based on the angular speed. They compute the position by integrating the value from these gyroscopes. These gyroscopes produce the angular speed, while the accelerometers, they measure the acceleration in the 3 axes. And from these 6 values, they can compute, actually, by integrating these 6 values, they can estimate the position and the orientation of your phone in the 3D space. And this computation is done on a DSP in a way that it would be the most energy efficient implementation, and it can be run in parallel to some useful application that is run on the main CPU, on ARM CPU. So this pre-computation, this, for example, determination of the attitude of your phone. So if I hold the phone in my hand, so the orientation of the phone relative to the surface of the earth is measured. So the 3 angles. So one angle this direction, one angle this direction, and one angle in this direction. These 3 angles can be estimated, measured based on the sensors that are implemented, that are available in these chips in your mobile phones. Processing is also used for the GPS signal, for this global positioning system. This signal that comes from the satellites is also being processed. Some part of this processing is done on DSPs. Okay. Going further, this slide describes how these DSPs are implemented. They can be a single chip solution. In this case, this DSP is similar to a microcontroller. So they have all of the peripherals. They have this CPU core. They have RAM and ROM memory. So all you need to have a complete computer system is available, and you can buy this chip. So this written on the right side were designations, the formal names or designation of these chips. So all of those were single chip solution as a DSP. But nowadays, these DSP are mostly some kind of ASIC cores. So this core can be licensable core. You buy a license for a VHDL description of a DSP core, and you integrate this IP, intellectual property, you integrate this soft IP core described through VHDL together with the rest of your design, digital design, a reminder of design. So you have this whole system implemented based on integrating several such IP cores. So you take the main CPU, VHDL model, IP core, you take DSP, you take buses, bus controls, RAM, ROM, and so on, and you implement it all together on some ASIC design. You have a solution that is customized to your particular application. These DSPs can be also implemented as soft cores on field programmable gate arrays, FPGA implementation of soft DSP cores, especially since these field programmable gate arrays nowadays they have a really enormous number of parallel multipliers and adders. This architecture shown on the whiteboard, this multiply and accumulator. Such architecture is available in field programmable gate array, not as a single solution, one such multiplier accumulator, but they have several hundreds of such multiplier accumulators available in this architecture that can be connected together into some useful design, in some useful algorithm, can be implemented to such architecture. So they have even much higher processing power than a DSP, because on a DSP, such unit is a scalar unit or maybe vector unit with several arguments, but finite number, small number of such scalar arguments. Two component vector or 4 component vector. So if it is some kind of synced architecture, single instruction, multiple data, this multiple data is a vector of 2 elements, of 4 elements, maybe 8 elements, but not more than that. On the other hand, on these field programmable gate arrays, you have the same basic underlying architecture of multiplier accumulator unit, but such units are, several hundreds of such units are available within one chip that can be connected into a very complex design. So for real-time processing of very high rate signals, if you are trying to have a processing of a radar signal or some signal, for example, this software-defined radio is nowadays also very active research field. Software-defined radio is how to implement a radio communication system, but that is implemented in a configurable hardware. And this configurable hardware, these FPGAs are almost ideal to implement such software-defined radio. Okay, so all of this architecture, they share the common idea as DSPs, but they are not a single chip CPU. They are dedicated hardware that is then designed, it is controlled by some state machine or by some host CPU, but it is not a standalone CPU. Okay. Going further, so this slide shows the market share in year 2004. So which were the main market players? We can see that the company Texas Instruments had at that time practically 1/2 of the market was for the Texas Instruments DSP chips. The company that is shown here, Analog Devices, is the one that we will use on our laboratory exercises. So this DSP, this Blackfin DSP, is produced by the company Analog Devices. And so 15 years ago, these Analog Devices had 1/10 of this market share of the DSPs. We also mentioned in this history slide this company AT&T that produced this first DSP-1. This company AT&T, Bell Laboratories, it was later on renamed this Agere, is this AT&T. It also had approximately 1/10 of the market in year 2004. It is also interesting to note that, for example, one of the most the most massive application of DSPs is not that expected, I would say. Practically, the largest market for DSPs are hard disk. So the mechanical hard disk, not the solid state disk, but the mechanical hard disk, where you have this disk with magnetic plates and these magnetic heads that are running over this disk surfaces, reading magnetizations, zeros and one, to control this magnetic head, the movement of this head along the disk surface, and to precisely position the head over one track on this disk. All of this feedback loop, the feedback loop for this positioning is performed using DSP. Also the signal pre-processing, so once you have this signal coming from the coil of the reader head, so you have this reading head on the hard disk, and the output signal is some signal that has the induction, magnetic induction related to the state of this 1 or 0, so how this information is written in this magnetic layer on the disk. So the signal that is used to read this value is then processed using DSP to actually decode the written value on the magnetic surface. And that is the reason why DSPs were used in mechanical hard disks. Okay. This slide shows here the main families and the actual implementation of this chip, whether it is a standalone chip or whether it is core or both. You can have both as a single chip or as a licensable core that you can integrate in your own design. Some of those are chips and some of those are both core as well as single chip solution. And the companies mentioned here are this Agere, so this is the same AT&T company but with a changed name. Analog Devices that we will be using for our laboratory exercises. Also ARM in the version of ARM9 CPU, in this ARM9 family, they also have integrated the DSP executional units and the corresponding instructions into the instruction set to be able to perform DSP-like functionality within this ARM9 architecture. So they wouldn't need additional DSP. They would be able to implement DSP algorithms, but within the basic ARM9 architecture. Infineon company, it is this Siemens Semiconductor that also changed name. Motorola was one of the first company in this DSP field, and this 56,000 DSP is still available as a chip. StarCore, Texas Instruments, and so on. Okay, and now we will try to describe the basic idea of these DSPs and their architecture on an example of one very simple DSP. This DSP is from the company Analog Devices. This family here, AD21XX, it is a fixed point DSP, and the data path is 16-bit wide. This 16-bit DSP is used, for example, in the low-cost MP3 players that you could buy for maybe $10 as a USB stick. So maybe 10 years ago, you would buy MP3 player that looked like a USB stick. So it was actually a flash memory. You could plug it into your USB port. You can simply copy your files to this USB stick. But it also integrates the MP3 player. So you were able to play MP3 songs, MP3 encoded songs that were written on this USB disk. So you had some simple user interface based on some LCD screen, based on few buttons. And through this simple user interface, you were able to select the song from the flash hard disk and to play it on this player. And this player actually was implemented exactly using this ADSP architecture that was at that time copied by the Chinese company and integrated with the controller. And the controller that was used was also copied the original architecture of Zilog Z80. So Zilog Z80 microprocessor, it was actually a microprocessor, almost single chip microprocessor, but the peripherals were implemented with additional chips. This Zilog Z80 was a very popular 8-bit microprocessor, and very early standalone computers in the early 80s or late 70s were designed exactly using this Zilog Z80 8-bit microprocessor. And this Zilog Z80 plus these Analog Devices, they were both, let's say, copied by the Chinese companies and integrated into a single chip solution that was combined with the flash drive. And this flash drive was then used for the storage of MP3 files, and you could then play this MP3 file, decode it in real time, and decoding was done on the DSP. So this DSP was used to do the real-time decoding of the MP3 audio stream that was read from the flash drive. Okay? Then going further, so how does this DSP21XX looks inside? So this block diagram shows the internal architecture of this DSP. First of all, from this image, we can see many executional units. So these three are execution units. These two above are also execution units, but related to address generation. They are dedicated to generate the address of the operand. So these are address generators. These three executional units are ALU unit, arithmetic logic unit, make unit, multiply accumulate unit, make, and shifter unit. So these are actually dedicated to execute the instruction. On the top we have the memory space, program memory space, and data memory space. So we have a separate memory space for program and for data. But the left one, the program memory space, was also shared as an additional data space. The idea was, why don't we use this program memory space as an additional data space such that we are able to fetch two arguments in a single cycle. So if this instruction is already fetched, if it is stored in some instruction register shown here, then we can use this data bus an address bus normally used to access the program memory. We can use these buses to access data space, additional data space. So one additional one data space is this one, dedicated data static RAM memory, and this program static RAM memory is a shared memory, shared for program and additional data space. And you can see here that you have double data buses and double address buses. So these two are data buses. One is for this data space. So this one is for the data space. And this data bus is for program space, or this shared program and data space. Okay? So we have two data buses. One here, one here. Also, we have two separate address buses. So one address bus for the data space, this one. So this is data memory address bus. The other one is program memory address bus. PMA, DMA. These are data bus, PMD bus, program memory data bus, data memory data bus, DMD. So two data buses, two address buses. If I can implement the algorithm using only the on-chip resources, so the on-chip program memory, the on-chip data memory, execution units, and other generators, I don't have to access some external memory. Everything is on-chip. I have these double buses, double data bus, double address bus. But if the capacity of the internal RAM is not sufficient, if I have to connect external RAM, then I have these multiplexers that connect this external RAM either to the program memory space or to the data memory space. So these two address buses are multiplex. So program memory space bus, program memory address bus, and data memory address bus are multiplex and fed outside the chip to the external memory. The same is for the data buses. So I can connect this external data memory either to the data bus of the data space or data bus of the program space. Okay? But the basic idea is normally I would try to fit the algorithm within the resources available inside the chip. And I would not use this external bus at all. And in this case, I could achieve the highest processing speed and the highest efficiency, since I don't have external signals changing state and causing dynamic dissipation. So the consumption of power. Okay? Okay, going further. We can also observe if I enlarge this part of the image, only the executional units. They are shown here. Allo unit, make unit, and shifter unit. Also here enlarged are these address generators, because these address generators, they are dedicated to generate two effective addresses in each clock cycle. So in each instruction cycle, in each clock cycle, I can generate two effective addresses. One address here and one address here. The first address generator always generates the address for the data memory space. So this bus is data memory address bus, data memory data space address bus. On the other hand, the address generator number 2 can generate the address either for the data memory address or for program memory address. So they can, this generator can generate the address for either of the buses. Okay. Why is this necessary? Because I would like to have two data access in a single cycle, two data fetches. I would like to fetch one argument from the program memory that is addressed by this data address generator number 2. And I would like to fetch one argument from data space that is addressed by data address generator number 1. And in this case, these two memories would emit two values. One 16-bit value from data memory space and one 24-bit value from program memory space. The instruction width is 24 bits. So this DSP has an instruction of 24 bits wide, but if this program memory is used for data storage, only the 16 uppermost bits are used, only the topmost 16 bits are used, the 8 last bits are ignored. So they are used only in the case I interpret this value as an instruction. If I interpret this value as a data value, only those 16 most significant bits of 24 bits are used as a data value. Okay? This unit here, bus exchange, is used if I want to cross from one bus to the other. So this bus exchange is like a short circuit. If I want to emit the value from one bus to the other bus, because I want to change the data space to program space, something like that, I have to exchange where the value is stored, then I would short circuit these two buses, and in this case, the topmost 16 bits of this program memory data bus are short circuited to the 16 bits of the data memory space data bus. Okay? Okay, but what you can see from this enlarged image, that each of these executional units has a dedicated set of registers. The reasoning about this register is the following. The instruction can be executed only for the arguments stored in these registers. The instruction cannot be executed for directly data coming from memory. For example, I address the memory location and I want to add this value from this address to some other value. Such instructions are not possible in the direct or indirect addressing. There are not such instructions in the data set, in the instruction set, that would do this kind of direct memory access as an argument for ALO instruction. So all ALO arguments must be first fetched into these input registers, and then these input registers are used as an argument for ALO instruction. The result of ALO instruction is stored in the result register. The same is for the MAC unit, the same is for the shifter unit. Now we will describe in more detail how this ALO unit functions. This ALO is the most similar to the conventional ALO unit you can find on a microcontroller or on general purpose CPU. Okay? This slide only says once more, so the basic architecture is you have ALO, arithmetic logic unit, you have make unit, multiply accumulate unit, you have this shifter unit, dedicated shifter unit. Normally, these shifter instructions are implemented in ALO on a conventional CPU. You have shift to the left by one, shift to the right by one, or rotate through carry. Okay, so these are typical shifting operation you have on the microcontroller. This one is a dedicated shifter. It is called barrel shifter because it is capable of shifting the value not by one position to the left or right, but by several bit position to the left or to the right. So, for example, you want to shift the value 5 bits to the left, or 5 bits to the right, or 17 bits to the left. So you can specify large number of bit position shifts to the left or to the right, and all of this is executed in a single cycle. So it is not executed 17 shifts by one, by one, by one. It is executed in a single cycle as shift by 17-bit position to the left, for example. So such shifter is then called barrel shifter because it behaves similar as a barrel on the pistol, on a Colt. If you have a Colt pistol, then you have this barrel, and you can rotate this barrel by any number of positions. So if you shift by 3 positions, for example, you have the desired position of the barrel that is shifted 3 positions to the left or to the right. Okay? And that is the reason, that is the cause why it is called a barrel shifter, because you have this kind of barrel operation. Okay? ALU. So this architecture of arithmetic logic unit, it has X branch, Y branch. So mostly ALU instructions are binary instructions. You have these 2 values, X and Y value, and compute, for example, add X and Y branch, or compute logical AND operation, or logical OR operation, whatever. So if you have this binary operation between 2 arguments, you have X and Y branch. X and Y branch come either from AX registers for the X case, or AY registers for the Y case. So left side, right side argument. Left side argument comes from AX0 register, AX1. I have 2 16-bit registers here, AX0, AX1. The same is for AY, AY0, AY1. I have 2 registers on the right side. I can take any of those 2 here, any of those 2 here, and I compute the ALU instruction. Then the result, the 16-bit result, is stored in register AR or in register AF. This AR is abbreviation for ALU result register, so AR. And this here is abbreviation for ALU feedback, so AF. This A result is useful if you want to store later on the result into data memory or program memory. Then this result bus, as we see from the overall architecture, this result bus is connected. Where is connected? The result bus. So this result bus is connected to this DMD bus, and I can use this DMD bus to store the value from result bus to any of the memory spaces, program memory space or data memory space. Okay? So this output registers, this AR is the output register connected to this result bus. But you can also see from this overall architecture that this result bus is shared. It is shared between all of these executional units. That is very useful because this result bus can be used as a left side argument. If I go to this architecture of AR, so this AR register can be used as a feedback, but on the left side. So for example, I compute something, I say AR is equal to AX0 plus AY0. And I have this result here. And this AR can be combined as an argument for the next instruction. And then the next instruction can be AR is equal to AR plus AY1. So once I add AX0 and AY0, I have this AR, and then next instruction might be add A1, AY1 as well. I will write it on the whiteboard. So the first instruction may be AR equal to AX0 plus AY0. And the next instruction can be AR is equal to AR plus AY1. So this left side argument can be either one of these AX register, AX0, AX1, or it can be also a result register, because I have this connection here. I have this MUX that feeds the result AR to the left side argument of ALU. Similarly, I have this auxiliary or feedback register. This AF can be also used as an output register. So I simply write AF is equal to some ALU operation. For example, I can use AX0 and AY1, okay, as an example. So I compute the logical AND operation between 16-bit value stored in AX0 register and register AY1. And now I can use this AF as a right side argument of the next instruction. So I can say maybe next instruction AR is equal to AF, not AF is on the right side, is equal to AX1 and AF. So now I use this feedback register as a right side argument and compute AND operation with, for example, AX1 register. And now I have computed AND operation between three arguments, AX0, AX1, and AY1. So I can use this feedback register as an intermediate value that is used as an argument for the next instruction. All of these instructions that I'm writing on the whiteboard are actually written as in algebraic form. So I have some kind of algebraic expressions. And why it is so? Because exactly the assembly language it has such algebraic notation. So it doesn't have this mnemonic type of notation that you can usually find on typical CPUs. So you have this Intel mnemonics or Motorola mnemonics or whatever CPU or microcontroller you use. You first have the mnemonic of the assembly instruction, then you have the input arguments, and then you have the destination register. But all of this can be also written in this kind of algebraic form. And this DSP for analog devices actually uses this algebraic form as a notation for the assembly instruction. Why? Because it was mostly suited for the scientists. So this DSP was suited for scientists or mathematicians or engineers, and these kind of users were accustomed to this kind of algebraic notation, and it is much easier to understand the assembly code when it is written in such a way than when it is written in a mnemonic notation. Okay, going further, so we have described the result register, we have described the feedback register. You can also write the value directly into the AR register by reading some value from memory. For example, AR is data memory address by pointer I0. We will show such instructions later on. So you have this direct path from the DMD bus into the AR register. It is used for initializing some value into AR register directly by skipping this normal ALU path through the ALU unit. So this ALU has one input flag, it is carry input flag, and it has 5 output flags, or 6. So the first 4 output flags are conventional flags that you have on most of the general purpose CPUs or microcontrollers. So this AZ is 0, AM is negative, AC is carry, and AV is overflow. So these are 4 output flags depending on the result of our instruction. If it is 0, it is negative, if you have carry, or if the result is overflow. You have one input flag, this C input. It is carry input. Okay? Then why do we use this carry input and carry output? For example, if I want to implement double word addition, if I want to add some values, for example, I have two 30-bit values, C high, C low, and I want to add this to D high, D low, D high, D low. And so how do I do it? I first take the lower words, I add them together, and I have this CL plus DL, and I store this to result low. Result low is lower words C, lower word D. But this might generate carry. And if I have this carry, I use this carry when adding up CH and DH. So when I add this up, I also use this carry from the addition of the lower two words. So this next instruction would also add carry from the previous instruction. And this carry is fed from this carry out, AC, as a carry in into the next instruction. So this next instruction might look, for example, if I have AR is AX0 plus AY0, that might be this C low plus D low. So D low and C low were stored in AX0 and AY0. And as a result of this instruction, I have this carry generated. And in the next instruction, I can compute, for example, AF is equal to AX1 plus AY1 and plus C plus carry. In this case, this AF would contain the upper word of the sum, and this AR would contain the lower word of the sum of these two double word arguments. Okay. It performs arithmetic and logic instruction. The arithmetic functions are add, subtract, negate, increment, decrement, absolute value, and division. It also has a division operation, but this division is implemented using a repeated execution of a division primitive. So you have one division primitive instruction that must be repeated how many times? Exactly how many quotient bits I want to compute. If I want to compute 16 quotient bits, I have to repeat this primitive instruction 15 times and one additional instruction one time. So first is to compute the sign bit, one instruction that computes the sign bit of the quotient, and then I have to compute 15 fractional parts, fractional bits, by repeating this division instruction 15 times. It is not very efficient, of course. It is much more slower than the multiplication, because the multiplication is done in a single cycle, but this division then requires, if I want to have a single precision quotient, I have to perform 16 instructions to get this 16-bit result. Okay, it also performs logic operations and or exclusive or not. As we said, it has left side and right side ports, X port and Y port. It has carry in input, carry in flag from the previous instruction. So this carry out of the instruction that preceded is used as a carry in for the subsequent instruction. And it is used to implement extended precision arithmetic in a single precision data path OWL. And as we described, it has this output register AR, 4 input register AX0, AX1, AY0, AY1. The return path, so the registers, the result register of this executional unit, but also of the other executional unit, can be used as a left side argument. So beside AR, I can also use MR0, MR1, MR2, SR0, SR1. So I can use these registers as output registers of the multiplier unit or output register of the shifter unit. I can also use these output registers as a left side argument here. So this result bus is a common bus shared along all of these execution units. Okay? It generates 6 output flags. It has also the so-called shadow registers. So this AX0, AX1, and AY0, AY1. They also have the shadow pair. This shadow pair is used to achieve very fast context switch. So once, for example, you want to execute the interrupt service request routine. And normally, when you have a general purpose microcontroller or CPU, once you service this interrupt, first of all, you have to store the context. So if some register would be destroyed in servicing the interrupt, if you use some internal register on the CPU, the initial value of this register from the main program must be stored. It is stored on the stack. And then, only then, these registers can be used inside this interrupt service request routine. At the end of this routine, the original values are restored in this register before returning to the main program. This context switch from the main program to the interrupt service routine and back to the main program requires many cycles. If you have to store many register values from the main program to the stack and from the stack back to the registers, and if you have this kind of shadow registers, this black one, so I have copy of AX register, I have a copy of AY, copy of AF, copy of AI. I don't have to do the context save. I only switch, either I use the white register or I use the black register. So as soon as I enter the interrupt service request routine, I simply switch the registers from white to black. I use the black register. And at the end of the routine, I simply switch back from black to white. In this way, I'm saving a lot of cycles that are normally used to do this context save and context restore when servicing the interrupt. Okay, now the emission will stop, so I will stop also for today. I will give you all the information about the video file that is stored. I hope it would normally appear on the web's page of this YouTube channel after the recording stops. These files are now organized into several playlists. Since we have these several courses that use this room, we have a different playlist for each of the courses, and ESD playlist will contain all of the recordings for this course. So that's all for me from today, and see you in 1 week time. And please do your laboratory exercises according to the assignments that you were given. So if you have any questions, don't hesitate to ask. The team channel will be active also when this YouTube channel stops. Okay, bye-bye.